Hi guys, we're going to do some extra practice with our graphing work today. So if you remember in our last set of notes, we talked about solving equations by looking at their graphs. So that's what we're going to do here. So for our first couple of examples, we have the graph provided to us. So for number one, I've got this quadratic function here, and there's my parabola. And I want to know, when is this equal to 0? So my parabola is already graphed for me. I want to know, when is it equal to 0? So I'm going to go to where y is 0. And then I'm going to draw my line all the way across so I can see every place where y is 0. Now, y is 0 on the x-axis. We did several examples of this in our notes the other day. So what we're really looking for anytime we're equal to 0 are the x-intercepts. So our solutions here, where our function, where our parabola is equal to 0, are going to be those x-intercepts. So 1 and 2 would be our solutions here. And again, we just want the x coordinates for those intersection points. For number 2, again, we have the graph of our parabola, and I want to know, when is it equal to 4? So I've got that line graphed here as well. So I'm looking for those intersection points right here and right here. And so again, we're just looking at, when are my x values the same for both of these? So this would be when x is -5, and when x is, that would be -2. So -5 and -2 are our solutions there. As we take a look at number 3, for the rest of our problems, we're going to have to create the graph. So we did a lot of practice with that over the last few days. So since I've got vertex form here, I want to point out the vertex. My vertex would be 7, -1. So I'm going to plot that point. 1, 2, 3, 4, 5, 6, 7, -1. That's going to be a point right there. And then I look at my lead coefficient to determine the shape of my graph. Since I don't see a number there, that means my lead coefficient is 1. And this is going to have the same shape as the parent graph. So that means up 1, out 1 for my first set of nice points, always counting from the vertex. Up 1, out 1. And then for my next set of nice points, up 1, 2, 3, 4, out 2. Again, always counting from the vertex. And there would be my out 2. So we're a little off the coordinate plane on the right-hand side here, but that's okay. So there's my parabola. And then I want to know, when is it equal to 0? So I'm going to go to where y is 0 and then extend my line all the way across the graph so I can see everywhere that y is 0. Again, since we're looking for when y is 0, we're looking for the x-intercepts. So that would be 1, 2, 3, 4, 5, 6. My solutions would be 6 and 7, 8. 6 and 8 are my solutions there. If you have not yet tried the rest of these problems, I want you to pause this video and go try 4 through 8. And now I'm going to go through 4 through 8 as well. So for number 4, again, we're going to start with our vertex. So our vertex here for our parabola would be -2, 4. So -2, 1, 2, 3, 4. And then we look at our lead coefficient to determine the shape. So our lead coefficient here is negative. That means that I'm going to open down instead of up. So all of the distances are still going to be the same. The only thing that will be different is, instead of going up, we're going to go down. So for my first set of nice points, down 1 and out 1. For my next set of nice points, I'm going to go down 1, 2, 3, 4, and out 2, again, counting from the vertex. And there's my parabola. Now I want to know, when is my parabola equal to 0? So I'm going to go to where y is 0 and extend that across my graph so I can see all those places where y is 0. And then I'm looking specifically for the places where I've got intersections with my parabola. So those solutions then are going to be, again, just the x part of those intersection points. So 1, 2, 3, -4 and 0. Are the solutions there. On the other side, number 5, again, we're starting the same way. I want to graph my parabola, so I'm going to identify my vertex. My vertex here is 7, -1. So I'm going to plot that. 1, 2, 3, 4, 5, 6, 7, -1. And then again, look to my lead coefficient to see the shape of my graph. Since I don't see anything there, that means my lead coefficient is 1, and I'm going to have the same shape as my parent graph. So up 1, out 1 on either side, and then up from the vertex, 1, 2, 3, 4, out 1, 2, and 1, 2 on the other side as well. So there's my parabola, there's my shape. And I want to know, when is my parabola equal to 3? Okay, so we actually graphed this problem with the other example. We graphed this exact parabola and we wanted to know, where was it equal to 0? Now I want to know, where is it equal to 3? So I'm going to go up to 1, 2, 3, and then draw my line all the way across. And I'm looking for those intersection points right here and right here. So my solutions would be 1, 2, 3, 4, 5, 5, and 6, 7, 8, 9. 5 and 9 are my solutions there. Number 6, same idea. I'm going to start by graphing my parabola. So that's on this side. My vertex would be -2, 4, -2, 4. So I'm going to plot that point, -2, 1, 2, 3, 4. And then I look to my lead coefficient to determine the shape. Since my lead coefficient is negative, that means we're opening down. So down 1, out 1, and then down 1, 2, 3, 4, out 2. So there's my parabola. And then I want to know, when is this equal to 3? So I'm going to go to where y is 3, 1, 2, 3, and I'm going to extend that all the way across so I can see all the places where y is 3. And then I'm looking for those intersection points. So right here and right here. Those x values then would be -1 and -3. So my solutions there are -1 and -3. For my last couple of examples here, number 7, I've got x squared plus 3 for that parabola part, for my quadratic part. Now, this is in vertex form, but I can't see the x coordinate like we could here. So that means that x had to have been in parentheses with 0. That's the only thing that could have been there that I wouldn't have to write. So that means the vertex is 0, 3. So I'm going to plot that point, 1, 2, 3. Since my lead coefficient is 1, that means up 1 and out 1 for my first set of nice points, and then up 1, 2, 3, 4, and out 2. So there's my parabola. And I want to know, when is this equal to 4? So I'm going to go to 1, 2, 3, 4 on the y, and then extend all the way across the graph. My solutions here are -1 and +1, since those are the x values for those intersection points. And then for our final problem here, again, this one doesn't quite look like it's in vertex form. We saw some problems like this earlier in our notes, but this one even looks a little bit farther removed from vertex form. It looks pretty similar to our parent function, but if I wanted it to look like vertex form, well, first I know, since I don't see x in parentheses with anything, it had to be 0. And then since I don't see that y component here, that means that also had to be 0. So here's a more vertex-y form of this function. So I can identify that my vertex is 0, 0. So I'm going to plot that point. And then since my lead coefficient is -2, that means 2 things. 1, I'm going to open down instead of up. And then 2, I'm going to be stretched. So all those vertical distances are going to be doubled since I have a lead coefficient of -2. So instead of down 1, out 1, we're going to go down 2, out 1. So from the vertex, down 2, out 1. There's my first nice set of points. Then for my other nice set of points, normally from the vertex, we would go down 4 and out 2. We're doubling that vertical distance. So instead of 4, we're going to go 8, since 4 times 2 is 8. So from the vertex, 1, 2, 3, 4, 5, 6, 7, 8, and then out 2. The amount I went out didn't change, just that vertical distance has changed. So there's my parabola. And then I want to know, when is it equal to -2? So I'm going to go to where y is -2, and I'm going to extend that all the way across my graph. And those are my intersection points there. So my solutions again are the x coordinates of those intersection points. So that would be -1 and +1. So there are my solutions there, -1 and +1. Okay, so that's some extra practice with solving by graphing.